Today, we want to go on to the next big thing. The next big thing is solving triangles. And at this point, you might be thinking, dude, was that not the first big thing that we had? Are we just doing this over again? Like, oh yeah, remember The Force Awakens? I'm just kidding. Before we were solving right triangles. That was a subset of this problem. We wanted to take the right triangles part out of it. We've solved right triangles before. Now we're going to be solving any triangles. So earlier we had solved right triangles before. Now we're going to be solving any triangle. In particular, we're going to have to develop a tool set for solving oblique triangles. Oblique triangles are just non-right triangles. An oblique triangle is a non-right triangle. Only one of our tools from before translates. The sum of the angles in a triangle is 180 degrees. The sum of the angles in any triangle is 180 degrees. That tool still applies. In an oblique triangle, we don't get to use the Pythagorean theorem anymore because the Pythagorean theorem is just for right triangles. In an oblique triangle, we don't get to use the Pythagorean theorem. That's for right triangles. If we have to say hypotenuse, we have to talk about right triangles. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Since we're saying hypotenuse, we have to be talking about a right triangle. Not a right triangle, not a hypotenuse, no Pythagorean theorem for you. We also don't get to use sine is opposite over hypotenuse. Once again, it says hypotenuse right in the thing, and we don't have a hypotenuse. We also don't get to use sine theta is opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and this actually includes tangent of theta is opposite over adjacent. Those ratios are for right triangles. if we take an angle in a triangle, there is only one opposite, but there are two sides that are adjacent. The reason that we get to say adjacent and opposite and hypotenuse is that we have one of the sides be the hypotenuse. Then we can say that the other one is adjacent. So in a right triangle, we have one of these sides we can call the hypotenuse. Opposite the right angle is the hypotenuse. Then when we look at theta, there's only one thing that we can call the adjacent side, because the other side that's adjacent to theta is the hypotenuse. And then this is, of course, opposites. There's only one opposite, but there are two adjacent sides. So one is the hypotenuse, the other one is just adjacent. So we don't get to use the Pythagorean theorem because we don't have a hypotenuse. We don't get to use our trig ratios. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. And tangent theta is opposite over adjacent. Those are tools for right angles, right triangles. Any questions? How's everybody, okay? Everybody sad at the loss of our tool set for solving triangles. Still works in right triangles. We're still cool with right triangles. So we have a new tool today. It's called the Law of Cosines. The Law of Cosines is the generalized Pythagorean theorem. The Pythagorean theorem when we ain't got a right angle. I want you to think about the law of cosines as being the generalized Pythagorean theorem. It's the Pythagorean theorem when we don't have a right angle. Here's how I need to set it up. I need to name the parts of a non-right triangle. Every time I try to draw an oblique triangle, it looks like a right triangle that I just kind of like rotated. I don't know why. None of these are right angles. I know you're all like, oh, that top one looks an awful lot like a right angle. Michael, it is not a right angle. You're like, well, it totally looks like it is not a right angle. So we're going to go with our usual. I'm going to call if this angle is alpha, then opposite alpha is A. Up here, we'll put the angle beta. Opposite beta is B. And over in this corner, we'll put gamma. Opposite gamma will be C. So angle alpha is opposite side A. Angle beta is opposite side B. Angle gamma is opposite side C. This is the standard setup that we're going to use. The other standard setup that happens is that we use lowercase letters for the sides and uppercase letters for the angles. This is great when you're reading and writing. It is terrible when you're talking because you say things like angle A is opposite side A, but it's a capital A for the angle. So you have to be like, well, angle A is opposite side A. Angle B is opposite side B. You have to like shout it. You know what I mean? And then people say, well, he was shouting, try to put an exclamation point. It's like, oh no, that's factorial. It's something completely different. So another setup that you might see is alpha or capital A, beta or capital B, gamma or capital C. C is also a terrible choice because when you're writing, it's hard to tell a capital C from a lowercase c. Unless you have very consistent sizing in your handwriting. Let's write down the law of cosines, which is going to be our generalized Pythagorean theorem. Start off by writing the Pythagorean theorem. C squared equals A squared plus B squared. But wait, there's more. So it's like the Pythagorean theorem with this extra term, minus 2ab times a cosine. Yeah. C squared is A squared plus B squared minus 2ab cosine gamma. Pause for comment. Now, when we look at this equation here, we say, dude, there is no alpha and there is no beta. But wait, there's two other versions of this. There's a B squared version where we say B squared is A squared plus C squared minus 2AC cosine of guess. What's the only thing that makes sense to put here? Beta. Because angle beta is opposite side B. But wait, there's more. Pause for copy. How many more are there? One. What's it going to start with? A squared. What are these two terms going to be? What's this one going to look like? And what's the angle going to be? It writes itself. Remember that cosine of 90 degrees is equal to 0. So if any one of these angles is equal to 90 degrees, then this term goes away and we're just left with the Pythagorean theorem. So it's completely consistent with the Pythagorean theorem. It's the generalized Pythagorean theorem. It's the Pythagorean theorem when we don't have a right angle. So cosine of 90 is 0. So if any one of these angles is 90 degrees, if gamma is 90 degrees, that makes C the hypotenuse, and we just get the Pythagorean theorem. If beta is 90 degrees, then B is the hypotenuse, and we get the Pythagorean theorem. If alpha is 90 degrees, then A is the hypotenuse, and we just get the Pythagorean theorem. This section is going to be really annoying because I have to say everything 3 times. This section is going to be really annoying because I have to say everything 3 times. I don't have to say that a 3rd time. I don't have to say that a 3rd time. I don't have to say that a 3rd time. Or did I say it a 3rd time? There are only 3 kinds of mathematicians, those who can count and those who can't. So this is the law of cosines. Step 1, being able to write it down. Recognizing that it's just an extra term on top of the Pythagorean theorem. Looking at the pattern, the form that it takes. Notice that C and gamma, if we put C squared on one side, it's gamma in the cosine parts, and in the middle is just A and B. There's also the B squared and beta one, the A squared and the alpha one. So the A squared and the alpha one, we have surrounding B squared and B and C. The B squared and beta one is surrounding the A and C. So look at the pattern. That will help you remember what the law of cosines looks like. The 3 different versions we use, the one that we use the C squared and the gamma one if we want to find C or gamma. We don't want to use this to find A or B. We can use it to find A or B, but I don't know why you would want to do that for yourself. So whatever angle you happen to have, that's the version that you want to use. So the B squared one is A squared plus C squared minus 2AC cosine of beta. Use that to find B or beta. The third one with A squared is equal to B squared plus C squared minus 2BC cosine alpha. We'll use that to find A or alpha. We'll use C squared is equal to A squared plus B squared minus 2AB cosine gamma to find C or gamma. We'll use B squared equal to A squared plus C squared minus 2AC cosine beta to find B or beta. We'll use A squared equals B squared plus C squared minus 2BC cosine alpha to find A or alpha. And right now you're thinking, dude, did you just trick us into writing the law of cosines, all 3 parts again? I'm like, oh, no. Yes, I 100% did that. Some of you are halfway through writing it and you're all, son of a bitch. How do we let you get away with this stuff? So we'll use this if we want to find, we can actually use this to find any angle as long as we have 3 sides. So that's one of the situations that we could use this. We could use this to find an angle if we have all three sides. We can use this to find a side if we have two sides and the angle in between those sides. But we can use this to find an angle if we have three sides. We can find a side if we have the other two sides and the angle between those sides. Two sides and the angle between those sides. So if I have A, B, and gamma, gamma is the angle between A and B. Beta is the angle between A and C. Alpha is the angle between B and C. Here are the two situations where we could use the law of cosines to find something. When we say the angle between those sides, we might say that call that the included angle. Two sides and the included angle. We have abbreviations for these two cases. Because this is math class and we'll have abbreviations for fucking everything. Three sides we call the SSS case. Two sides and the included angle is two sides and the angle between them. So SAS case. In case you're worried, the two sides and the unincluded angle is the SSA case. We don't write that the other way around. But strangely enough, that is the way you will think about it. Take a break and come back and do some examples. Let's do a couple of examples of using the law of cosines to solve for parts of an oblique triangle. So in the first setup, I've given you A and C and angle beta. I've given you two sides and the angle included in those sides. Two sides and the angle included in those sides. This shows up because we have an A and a B and a C. We have one from each of the letters. A, a B, and a C. A, side A, angle beta, and side C. If we look at the generic drawing of our triangle, we have side A and side C, and beta is the angle included in those two sides. So this is the SAS case. At this point, the only thing that we can use this information to find is side B. B squared is over here. I've got A, C, and angle beta. So we're going to find B. So in this case, since I have A and C and angle beta, that means we're going to use that second version of it, the green line, to because that's what we use to find B or beta. Since we have beta, we're going to use it to find B. We're going to write B squared is equal to A squared plus C squared minus 2AC cosine of beta. At this point, you're like, oh, dude, did you just get us write the second part of the law of sines again? I'm like, oh, yeah, totally. This is called mind control. I'm just kidding. Some of you are like, oh, I'm not writing it again. I'm just going to look at it. So we're just going to be plugging the parts in. So this next one, I'm not going to just write the generic one again. I'm actually going to be plugging numbers in, but I'm going to start by writing B squared equals. So B squared I want to write this one time. I don't want to know what B squared is, right? I didn't say find B squared. I said find B, right? To find out what B is equal to, I need to take the square root of both sides. So here's what we're going to write instead. We're going to say B is equal to the square root of A squared plus C squared. So A is 12.8 squared plus C squared, which is 7.65 squared, minus 2A, 12.8, C, 7.65, times the cosine of 57.3. Pause for copy. Then we're going to grab our calculating machines and calculate. The nice thing about using the law of cosines to solve for a side is once we put the square root in, we just have to type it like we see it. Oh. I like how the calculator tells me what I need to do. It's like, well, the battery is low. We recommend that you charge the battery. It's like, no shit. I know how batteries work. It's 2024. We all know how rechargeable batteries work. If you have an older version that actually has batteries inside it, so batteries are low, we recommend you change the batteries. I actually got to give them props because Texas Instrument is a company that does exist to make money. So they could have been like, oh, your batteries are low. We recommend you buy a whole new calculator. So I guess I appreciate the avoidance of just naked, horrible capitalism. I'm just going to type this in like I see it. I'm going to type a square root. So square root of 12.8 squared plus 7.65 squared minus 2 times 12.8 times 7.65 times the cosine of 57.3. Before I hit enter, I'm going to make sure that I am in degree mode because the 57.3 is in degrees. Then we're ready to hit enter. B is 10.8. I didn't say to round your answer to 3 significant figures, but the two sides are in 3 significant figures. Heck, the angle is still even in 3 significant figures. So let's just write 3 significant figures. Let's just try to make it fit in. Any questions? One of the things that we want to notice is that given side A and side C and angle beta, this was our only option. Partially because we only have the law of cosines right now. But when we first encounter a problem, sometimes we'll only have one thing that we can go look at for. And only one way to get at that thing. Any questions? Using the law of cosines in the side angle side case, two sides and the included angle is the easiest way to use the law of cosines. So that will be our favorite. All right. So here I have given you the three sides of our triangle, and we're going to use the law of cosines to find an angle. The good news is we can use the law of cosines to find any angle that we want. The bad news is we can use the law of cosines to find any angle that we want. We just have to pick one. I'm going to pick one for you, and I'm going to say, let's find alpha. Actually, I'm going to change that. I want to find gamma first. The reason I decided to switch to gamma and find gamma first is that gamma is going to be the biggest angle in this triangle. If you have to choose, pick the biggest angle. So A is 8.12, B is 5.76, C is 11.4. So opposite C is gamma. Opposite the biggest side, you'll find the biggest angle. Go for, if you have a choice, go for the biggest angle first. This is called prison rule. If you have a choice, find the biggest angle first. Let's find gamma first. Since we're looking for gamma and we have three sides, we're going to use the law of cosines. We have the side, side, side case that says to use the law of cosines. We're going to find gamma. So we're going to use the version of the law of cosines that has C and gamma on the outside. So we're going to use this version of the law of cosines. For those of you who don't want to write it again, but are just automatically copying, stop automatically copying because I'm just going to write the first law of cosines again. I want to start from here. C squared is equal to A squared plus B squared minus 2AB cosine of gamma. I said find gamma. We have to use the law of cosines part that has gamma in it. This is really set up to find the side very easily. This is very easy to find C. Just write a square root on both sides. we want to rearrange this so we can just say gamma equals, because we want to plug just one thing into our calculator. We want to hit enter on our calculator one time, especially right now, because I'm almost out of battery. So what we're going to do is I'm going to take the a squared and the b squared terms. I'm going to put them on the side with c squared. So I'm going to write c squared minus a squared minus b squared is minus 2ab cosine gamma. Everybody see what I did there? It's a little algebraic sleight of hand, nothing up my sleeves, presto. I want to get gamma by itself. That means I have to get cosine of gamma by itself first. I've got to get rid of the negative 2ab. That's being multiplied by cosine of gamma, so I'm going to have to divide by negative 2ab. So I'm going to say c squared minus a squared minus b squared divided by negative 2ab is equal to cosine of gamma. Negative 2ab, that's all being multiplied by cosine of gamma, so I'll divide that, and that's what it looks like. Now we're going to look at this and say divided by negative 2ab. There's only one term in the denominator and it's negative. That looks like trash. I don't know if you have an opinion on the aesthetic value of having a negative, or the aesthetic ugliness of having a negative monomial in the denominator, but it looks bad. Just look at that. This is bad. Ugh. Everybody just practice that simple. Ew. Ugh. Ooh, a negative monomial in the denominator. Ugh. When someone shows up at the party and they have a negative monomial in their denominator, you should be like, oh my gosh. Have you seen that fraction over there? So what we're going to do is we're going to change all the signs. Generally, I'm not a fan of just like make everything positive. Like if you sad for reasons, just be sad. That's fine. It's a valid thing. But I just don't like that. I'm going to make that positive 2ab, and I'm just going to change all the signs in the numerator. Negative a squared, no, positive a squared. Negative b squared, no, positive b squared. Positive c squared, nope, negative c squared. Then if we want gamma, we just cosine inverse of both sides. The reason that I did this instead of putting the numbers in first and then doing this is that I can translate this to cosine of beta or cosine of alpha. It's easy to translate to the other versions. So if I want to know what gamma is, I'll do a cosine inverse of a squared plus b squared minus c squared. A is 8.12 plus b squared. B is 5.76 minus c squared. And we'll divide by 2ab. 2, a is 8.12. B is 5.76. Since the numerator has multiple terms, we need parentheses. Since the denominator has multiple factors, we need parentheses. So notice I've got numerator parentheses. And we've got denominator parentheses. And the reason I wrote it this way is that this way I could just type it like I see it. So I'll do cosine inverse of numerator 8.12 squared plus 5.76 squared minus 11.4 squared. Close the numerator, divide by, open the denominator, 2 times 8.12 times 5.76. Close the denominator, close the cosine inverse, hit enter, 109.3. We'll write 109. Keep it to 3 significant figures. Make it look like the other one. Any questions? We can write 2 other versions for beta and for alpha. So we could also write cosine of beta. Instead of a squared b squared minus c squared, the negative one is the one that goes with the angle. So I'll have a squared plus c squared minus b squared over 2ac. So that would be the beta and b version of finding an angle. We can also do an alpha version. Right, cosine of alpha is b squared plus c squared minus a squared over 2bc. These are handy ways to remember these. These versions of the angle part of the law of cosines. This is the way we could write it. It's handy because that's how we type it. How's everybody okay? So if we wanted to practice this, we could actually use these same 3 sides, just rearrange them and find angle beta. So for angle beta, I would want the numerator to have a squared plus c squared. So 812 squared plus 11.4 squared minus b squared, 5.76 squared. Close the numerator, divide by, open the denominator, 2 times 8.12 times 11.4. Close the denominator, close the cosine inverse, and that's what we have for beta. At this point, if we have 2 angles, we could just subtract, find the 3rd angle. But if we're like, oh no, the law of cosines is super awesome, we could just do a cosine inverse of b squared and c squared. 5.76 squared plus 11.4 squared minus 8.12 squared. Close the numerator, divide by, open the denominator, 2 times 5.76 times the 11.4. Close the denominator, close the cosine inverse, hit enter, and realize I made a typo. Forgot to open the numerator. Any questions? All right, so that's the first tool that we have in our toolbox for solving oblique triangles. We can only use it in these situations. If I gave you side A and angle alpha, law of cosines, we can't use that. And technically, we could, I guess, define B or C, depending on what other side I gave you, but we won't want to. Question? Comment? Yes. Yes, if we don't actually, if I gave you like a 3, 4, 5, and you went to find the angle, it would work out to 90 degrees. It might happen to be a right triangle. So if A is 3, B is 4, and C is 5, then when you solve for gamma, it would end up being 90. And at that point, it'd be like, oh, it was a right triangle all along. And then it'd be a big dramatic reveal. And it's like, oh, wow, it was the friends that we made along the way. That's the real treasure. So yeah, absolutely. All this is backwards compatible, but we start with solving right triangles because it's easier to work with. And it gets us into it's a better introduction to trigonometric functions. How's everybody okay? So if you want to test it out, if we say A is equal to 3, B is equal to 4, and C is equal to 5, we might not recognize this as a Pythagorean triple. Given a choice, the first thing we would do is we would want to find gamma, and we would calculate gamma equals, we would do some stuff, and it would come up to 90 degrees. And at that point, you would have audible gasp. Oh, it was a right triangle the whole time. And then you could have dun, dun, dun. Any questions? Huh? Anyone want to guess what the next tool we're going to have? This one being the law of cosines. There's also a law of sines. No surprises there. Then we'll have enough tools to solve any oblique triangle. But not until Tuesday, because you never do law of sines and law of cosines on the same day, unless you want your class to get together and like disappear you in the forest. That's it for today. I will see you all on Tuesday. Everybody have a good weekend, and thanks for playing.